Thank you so much, Mika. Can everybody hear me? Yes. Thank you so much, Mika. Good afternoon, everyone. Thank you all for taking the time to come to my PhD defense, and I'm happy to be here today. Thank you to the jury members for giving me the opportunity to present my work. And today I'm going to talk to you about what I've done in the past 4 years. And the title of my talk, as you can see, is The Multiplicity of Galactic Wolf-Rayet Stars. So I'll take you through this. I'll explain what I mean by this, and let's get started. So astronomers love to put things in boxes. We love to classify stuff and whatever we see at. So if you look at a particular cluster, Omega Centauri, you can see that the stars that you look at are not all the same. Some are brighter, some are fainter, and they have different colors. Now, we astronomers obviously like to put the blue stars on one side and the red stars on the other side. So that's the x-axis, which you have color. Then we can also classify them according to their intrinsic brightness or their luminosity. And then we end up on something that looks like this. And we use this to look at stars and to study their evolution. So this is called the Hertzsprung-Russell diagram, named after Hertzsprung and Russell. And on the x-axis, instead of color, so color represents the temperature of a star. And on the y-axis, the intrinsic brightness is represented by the luminosity. So the scale is such that our sun is over here. So our sun is at 1. And you can see that most of the stars lie on this diagonal, well, let's say a bunch. And we call this the main sequence. So that's where stars spend most of their life, living on the main sequence. And after they evolve off the main sequence, they can appear as giants, supergiants, and red or blue supergiants. And then some of them end their lives as white dwarfs. Yeah, so the colors of and also the luminosities of the stars also means that they come in different sizes, and we classify them according to these letters that we have not arbitrarily, the letters that we've assigned to them. And so you have O and B stars that are quite massive. We know that they're quite massive. And what do I mean by massive? They have initial masses. So when they're born, they have masses greater than 8 times the mass of our sun. And then you have the low and intermediate stars, mass stars, and our sun is a spectral type G. So that's what you see over here. Now, I'm going to focus on massive stars for the remainder of the talk. So let me take you through how they evolve and how they live and how they die. So imagine a cloud of gas and dust that is extremely vast. So it's a protostellar nebula. So inside this nebula, you can have hundreds and thousands of or millions of gravitational instabilities that can occur at any point in time, which can cause material to collapse towards a certain point. Now, after a lot of time, and in astronomy, we usually like to judge things after a lot of time, what happens is that a star is formed. And a star is formed when inside its core, it's able to, so nuclear fusion takes place, where it's able to fuse hydrogen into helium and heavier metals. So for now, I've shown you an O star, and an O star will then, at some point in its lifetime, appear as a Wolf-Rayet star. And these are the objects that we are looking at. So you're looking at quite evolved stars. So they're old. In terms of the human age, they're about to die. Let's say they're quite up there, depending on where you live. And then the end stages of these stars are quite diverse. They are quite uncertain as well. So they can explode as a supernova, and then you have a supernova remnant, or they can direct, and then the remnant is then either a black hole or a neutron star, depending on whether it's an O star or a B star that we're looking at. They can also directly collapse into a black hole, but when what happens is not quite certain, and it's still an ongoing topic of research. So why do we care about massive stars? We have our sun, it's nearby, it gives us light, heat, and energy. Why do we really care about what happens, God knows how far away? We care about them because these massive stars, they are factories. They produce a lot of heavy elements that we have today on Earth, in our sun. It's all a result of massive stars. They were the first stars after the Big Bang, and they were probably extremely massive. So understanding how massive stars evolve will help us understand more about what happened directly after the Big Bang. They, in life and in death, they enrich their surroundings with energy, momentum, and chemicals, because whatever they produce in their cores is expelled outwards, either through the supernova that I was talking about or through their strong winds. And lastly, but not the least, they are the progenitors of black holes and neutron stars. So when they die, they leave behind these sort of objects. And these are quite exotic objects that we are not quite sure what happens. And we still need to learn a lot about these objects. Moreover, in binary systems, these neutron stars and black holes can merge and produce gravitational waves, which has been causing waves in our community for the past 5-6 years. So one topic that I like to introduce you about is spectroscopy. Spectroscopy, in a sense, we split light into its components, into its different colors, and then we study that. We look at it. So I like to take this as a life lesson as well, because in life, breaking down a problem into its components is always the way to tackle. And I would say that this actually, you can go quite deep into this, to the point where this is, if this image looks familiar, it's because it was also an album cover for one of the greatest of all time. So who says science cannot be fun? Now, over here, what you see is the spectrum of the sun. And the official title of this plot, of this image, is called the barcode of the sun, which I think is quite appropriate because it looks like a colorful barcode. Now, why do we not see a continuous, like a rainbow? Why do we not see a continuum here? Why do we see certain bands? So you see these certain dark bands because as the light from the sun reaches us, it passes through the photosphere of the star, of the sun. And in the photosphere are a lot of elements: iron, nickel, silicon. And these elements, these ions, they absorb photons of particular energies. And these energies, they correspond directly to particular colors. So on top, what I've done is taken a bit of the spectrum of the sun and taken it from a color and intensity, a two-dimensional plot, to a one dimension. And in that, what happens on the y-axis, you have the intensity of flux, and on the x-axis, you have how we like to represent color in wavelength. And so over here, you can see that, for example, this line over here tells us that there's hydrogen present in the sun. And that's also something that we know. And a lot of these lines are ion lines, some of them are nickel lines. And so by studying the spectrum, we can know what is inside. We can see the composition of the star. So similarly, different stars of different spectral types have different barcodes. Of course, if you go to the supermarket and you pick up a product, it'll have a different barcode because it's a unique product. It's a unique barcode to each specific element, to each specific item. Similarly, the spectra of different stars are similar, but so all O stars will have a similar type of barcode, but not exactly the same. So you can see that this barcode changes as you go across different spectral types. And I'd like to draw your attention that different spectral types refer to different colors and different sizes. So again, we're focusing on O and B stars, massive stars, and that brings us to Wolf-Rayet stars. Because when we talk about Wolf-Rayet stars, we need to know where they come from. So meet my good friends, just kidding, not my good friends, Charles Wolf and George Rayet. So in 1867, they were studying the constellation Cygnus. They were studying a couple of stars over there, and they identified three stars which had weird spectra. Now, I'm not going to show you spectra from 1867, A, because I do not have them, and B, because I have something else. So the spectra of these stars looks something like this. So as compared to what you saw for the sun, where you had absorption line profiles, so there was a dip in the amount of light that came out from the star, you have emission line profiles. And these emission lines are quite broad as well. So before we saw, I think, a 10 or 20 angstrom snippet where you had dozens of absorption lines. But here you see these absorption lines are quite broad. And you can see that I've put some identifications here. So to identify the elements that are present in the spectrum, we see mostly carbon and a little bit of oxygen and some helium, or we see nitrogen and helium. So depending on that, again, I'm going to sound like a broken record. Astronomers like to classify stuff. We call them WC and WN stars for carbon-rich and nitrogen-rich Wolf-Rayet stars. That isn't enough, obviously. We have to break that down into early and late type. And don't worry, early and late types are also broken down into 2, 3, 4. So that's just how much we like to break stuff down. Of course, you're not here to see spectra, you're here to see pretty pictures. And this is what I present to you. That's also one of the good things about studying Wolf-Rayet stars. Whenever my friends ask me, what do you do? I can just show them pretty pictures, because these are actually the nebulae that you see around Wolf-Rayet stars, not only in our own galaxy, but also in other galaxies. And we think that these nebulae are a lot of the mass that has been lost from the star, and due to their strong winds, it has been driven out into the surroundings. So by studying nebulae is also a way to study the history of the star. What happened? How did it happen? So that's something that also one of the jury members who is online is working on that right now. Um, Okay, so to recap, Wolf-Rayet stars, first observed by Charles Wolf and George Rayet in the Cygnus constellation in 1867. They have strong and broad emission lines of carbon or nitrogen with helium, and they have extended spatial features due to their strong mass loss. So that gives you a history of the mass loss. Now, we're going to look at the evolution of a Wolf-Rayet star from the Hertzsprung-Russell diagram. It's something I showed you earlier. So on the x-axis, you have temperature, just to remind you, which is also color. So from the right, which is cool temperatures, to the left, which is hotter temperatures. And on the on the x-axis, yeah. And on the y-axis, you have the luminosity. So if we look, so these Wolf-Rayet stars are in the green, like it's a green line. So this is the phase where they appear as Wolf-Rayet stars. So they are quite hot and they are quite luminous as well. We are following the evolution of a 30 solar mass star. So initially it had a mass that was 30 times the mass of our sun, and we call these O-type stars. When it evolves to the right of the diagram, so it becomes cool and still luminous. So the star expands, and at some point through some mechanisms which are still hotly debated, it sheds its envelope. So it sheds the cool layers of the star, and then it still remains luminous, but it's quite hot. So on the diagram, it travels all the way to the left. And this is when it appears as a Wolf-Rayet star. Now, the end stages are, as I mentioned, still a topic of debate, whether they directly collapse, whether there's a core collapse supernova. We are still not quite sure. The main question is, how do they strip their envelopes? How do they get rid of the cooler layers that are around the core of the star? And there have been two channels that are proposed, and this is again an open question in modern astrophysics as to whether they are formed with the help of a companion or whether they're able to do it by themselves. Are they strong and independent, or do they prefer companionship and somebody else to help them out? So in a binary system, you can have two stars that are close together, and the initially more massive one will evolve faster, and as it does, the secondary is able to strip the outer envelope, where it appears as this pink Wolf-Rayet star. And you can see that in this evolutionary channel, it appears twice. So this is an evolutionary channel proposed to produce gravitational wave progenitors. So in the single star scenario, you can have an O star that evolves into a supergiant, so very big, very cool, and through its own mass loss, either smooth or in eruptions, it can shed its outer layers and then appear as a Wolf-Rayet star. Now, which one of these scenarios, the binary or the single star, is the right one, or is the dominant one, let's say? There's no right answer here because both of them occur in nature. The interesting point is that Wolf-Rayet stars come from O stars. And if we look at O stars, they like to live with at least one companion, bound by love. That's not true. They're bound by gravity. And the thing is that these stars are in such short periods, so they are quite close together. So then they tend to interact with each other over the course of their lifetime. And some of these interaction products can look like this. So they can either come into contact, or one can transfer mass to another. So it's still not quite sure uh, what exactly happens in what configuration, because there are so many parameters to explore that this is still quite computationally intensive as well. But we do know that, thanks to Hugues and a lot of other researchers in our field, in the past decades, we know that most main sequence O stars exist in binaries. So if they all exist in binaries, what happens? Are they able to strip their own envelopes, or do they need a companion? So the answer to that is what we thought was to look at the binary fraction of galactic Wolf-Rayet stars, and then see, okay, if they start out in binaries, and if they are currently in binaries, we can understand what fraction of them are in binaries, and sort of in population synthesis, we can try to model what happens using different physics. And this will help us to constrain not only the physics of interaction, but it can also help us understand whether like the other, yeah, it can also help us derive the masses of these Wolf-Rayet stars, which is very interesting and important. Okay, so with this in mind, we started a spectroscopic survey using the Hermes spectrograph, which is mounted on our own Mercator telescope on La Palma. I love La Palma. I've gone there every year, and I would love to go there. And it's quite amazing, and it's amazing that we get the opportunity to use this instrument and this telescope. Anyway, so we got around 39 Wolf-Rayet stars with the spectral types indicated over here, and about 12 WC stars and 27 WN stars. Math is hard, sorry. And oh, sorry. Yeah. And then what did we do with these spectra? We measured radial velocities. Now, another concept incoming. So if you have a binary system with two stars that orbit their center of mass, the top panel is the top view from above the orbit, above the plane of the orbit, and the bottom one is in our line of sight. So these stars will move back and forth in our line of sight, and as a result, their spectra, the spectral lines that we see, either in absorption or in emission, will wobble back and forth. And we can use this wobble to determine a velocity, which we can plot over here. So on this graph, you have speed or velocity as a function of time. And depending on when we look at the star, or when we take a spectrum of the star, we can catch it at different velocities. So that's pretty cool. So why is it interesting? Because if these stars are in binaries and we look at it over a certain period of time, then we should see some sort of motion. We do not know what the orbital period is ahead, well in advance. So we sort of devise a strategy where we aim to get at least 6 epochs per object. So these are some of the stats. We got 1,340 spectra over 5 years. We aim to get at least 6 epochs per object, but in some cases we are lucky enough to get more. And we aim to get a high signal to noise in the continuum region, around 5,000 angstrom. So the high signal to noise, so this is not, for people who work with spectra, you know that this is not incredibly high, but it is still high enough that we are able to identify any companions that might be lurking in the spectra. And it's high enough for us to derive accurate radial velocities. So on to some results then. Oh, excuse me. I do not want my laptop to die out on me right now. There we go. Right. So on to some results. So these are some results from the work that we've done over the years. So and this is a bit of a complicated plot, so let me take you through it. On the left side, we have something for the 12 WC stars in our sample. And on the right, we have this plot for the 27 WNs in our sample. Now, for each object, I told you we measure radial velocities at least 6 epochs. We can get an amplitude, the maximum difference in the radial velocities. That tells us that this is the minimum amount your star has moved over the course of 3, 4, 5 years, how many ever years you've looked at it. Now, we say that, okay, suppose my star has moved, let's look at this guy, WR137. It's moved about 25 kilometers per second. And I say, okay, my star has moved 25 kilometers per second over the 3 years that I've looked at it. Does that mean that this motion, this velocity that I measure, is it due to the fact that it's in a binary system or not? Because of course, there are some uncertainties on the measurements that we have, and it's important to understand and identify them. In the end, what we did through a lot of discussion, we decided to take a threshold of 10 kilometers per second for the WC stars and 50 kilometers per second for the WN stars. Now, I know 10 kilometers per second seems quite low, but the exact number that we choose for our threshold does not really matter, and I will explain that in a minute. So basically, now that we choose our threshold, let's just say that we've chosen 10 kilometers per second. We know that all of the stars on the right side are quote unquote candidate binaries because they have a large radial velocity motion that we consider it to be due to Doppler motion in a binary system. And in bold, you have some of the binaries that were already confirmed in the literature, both for the WN and the WC. And so you can say that, okay, yeah, your choice of threshold is definitely influenced by the fact that you have some of these binaries in the literature, and that is true. Now, what happens because of that? So on the y-axis, you see the observed binary fraction. And remember, that was our question in the beginning. What's the binary fraction, right? So can we just say that, yeah, these are the numbers. Good job, everybody. Let's go home. Is that it? Do these observed binary fractions tell us the percentage of all Wolf-Rayet stars that are in binaries? And the answer to that is no. One does not simply get the intrinsic binary fraction. And so in order to correct for some observational biases, because when we look at the sky, we're obviously not looking at each of the stars at every point in time, and we don't have an infinite amount of time to spend staring at them. So, and also these binary systems can be configured in any way and any orientation on the sky. So that's also very important. So we need to correct for some observational biases. In order to do that, we divided our stars into different bins that are given by different colors. So for example, let's look at the plot on the right. We have about 16 stars which have velocities delta RV, so the amplitudes between 0 and 50 kilometers per second. And then we have about 7 between 50 and 250 and so on. And then what we did is we used Monte Carlo simulations with Bayesian statistics to calculate and simulate what binary fraction would we need of the population and what sort of orbital periods would we need. Would they need to be super close? Would they need to be far away? What would we need in order to reproduce what we see? That was the one question. And if this sentence seems complicated, and if this seems a bit unclear, I apologize. I have come prepared. We give the code, not me, obviously. We give the code a bunch of delta RVs, and we say, okay, if I give you this, you are going to simulate and calculate and tell me what is the probability of me getting a particular binary fraction with a particular period distribution. Bayesian statistics forever. Yeah. Okay. So the output of this is the intrinsic period distribution. And it's a cumulative distribution. So let me introduce this plot to you. On the x-axis, you have the orbital period in log scale. Why? Because things look prettier in log scale. Everything looks like it fits in log scale. That's why. Okay, so over here you have orbital periods starting from 1 day to 10,000 days and 100,000 days over here. So that's how close together the binaries are. These stars in these binaries are, or that's how far apart they are. And on the y-axis, you have the fraction, the cumulative fraction. So what this means is that if you look at the blue curve, as you go from 1 day to 100 days, there are not a lot of systems. The dashed line and the solid lines are the best fit what we get out of our Bayesian simulations. And the shaded areas are the uncertainties due to a lot of assumptions in our models. So what you can see is that if I just followed the dashed line, as I go from 1 day to 100 days, I don't have a lot of binaries in my sample. However, if I go from 100 days to 1,000 days, I suddenly get a lot more systems in my sample. The fraction is increased from, let's say, 5% to about 25%. And then if I go from 1,000 days to 10,000 days, I suddenly get a lot of systems in my sample. And why does the code give us this? So it's important to understand what the code gives you, and not only that, oh yeah, it gave me something. So the code gives me this because in our sample of 12 stars, we had 2 or 3 of them that are on very long periods. So 3 out of 12, that's already quite a high fraction of them are in long period systems. So the code says, aha, if we've already found 3 of them in long period systems after only looking at them for 5 years, then there must be a lot more of them. And this is why we get this sort of a curve. But of course, the uncertainties on our models do leave some room for more short period binaries over here. Now, onto the red curve, which is for the nitrogen-rich Wolf-Rayet stars, the WNs. We see that it's sort of the exact opposite, where between 1 and 10 days, you have a large fraction of systems. So these are all binaries that are in very short periods. And okay, this is quite different from the WCs, but we know that they are linked evolutionarily. And then we see that as we go from about 100 days to 1,000 days, you still have some of them, but not a lot of them. And in crosses and plus signs, you see what we get from the literature. And of course, the literature doesn't give us 100% of the binaries, because as I mentioned, we are not able to identify all of them with the observational time span that we've had in the past couple of decades. So if that was too complicated, here's another meme. There are not a lot of long period WNs. Is that a problem? Not really, because they are probably there, but we just can't see them. But there are not a lot of short period WCs. Is this a cause for panic? Not really, because we've looked at the northern sample of Wolf-Rayet stars, in the northern galactic sample of Wolf-Rayet stars. We need to look at the south as well, because we know from the literature that there are a lot more short period binaries in the south. And therefore, if we look at the southern sample and we start an equivalent, a complementary radial velocity survey, then we'll be able to get a sort of a homogeneous result for the entire galaxy. So in conclusion, what did we learn? That the multiplicity properties of galactic WN stars are similar to that of O stars. So O stars are also in short binaries, as I said, because they interact. And we found that a lot of the nitrogen-rich Wolf-Rayet stars are also in short period binaries. That's good. That means all is good and dandy, and we can explain everything with our current understanding of binary evolution. The WC population has a significantly different peak of the period distribution. So most of them are at very long periods. But whether this is entirely due to the fact that we are only looking at the north, or is there another evolutionary channel that we are missing, or some sort of explanation that we still don't grasp, that is still to be investigated. And the differences between the WC and WN distributions are intrinsic to the populations. They are not. So what we've observed in the northern galactic sample is that the period distributions are different. and that's not an observational bias that is intrinsic to these populations. There is a significant lack of short period binaries, which either we can explain due to a lot of exotic stuff like mergers, disruption of the systems, maybe some triples if you fancy some spice in your science. But of course, we should also keep in mind that we are only looking at the northern sample and not at the southern sample. So to conclude, I would also like to say that because I'm an astronomer and I've been doing, a lot of my friends are very happy or like excited that I'm an astronomer. One of the questions that I get the most, Karan, when are you going to find aliens? Jadoo kab aayega? And to them, I say this. Thank you so much for listening to me. I will leave you with my conclusions. I think the jury cam is here.
Thank you. Oh, the camera is here. Okay.
Yeah.
Don't like cameras. Okay, now we turn to the question part. And once more, I'd like to introduce you to the jury members. So we have Professor Paul Kroter from the University of Sheffield. We have Professor Nicole Saint-Louis from the Université de Montréal. Then we have Dr. Pierre Haré, who is apologized. We have Dr. Professor Jon Sundqvist from KU Leuven, and we have the two supervisors, Professor Hugsal.
Thank you, Karan, for your very nice presentation. So I've got a few general questions and a few specific questions. The general question is, imagine a universe without massive stars. How would it differ from our present universe?
Well, I think that we not have a lot of the heavier elements that are usually synthesized in either through the supernovae of massive stars, especially like through rapid or S process or not S process, like the R process, basically whatever is produced during the supernova itself. A lot of these heavier elements are synthesized and then expelled out into the interstellar medium. So I think we would definitely lack those. And also the most massive stars also produced a lot of the ionizing flux. And I think we'd be missing a lot of that as well. So the history of the universe would be completely different.
Sure. But I guess these sound like quite exotic elements. So any very important elements for life that might have a relevance for massive stars?
Well, I mean, through hydrogen burning, we also have like nitrogen that is produced, and 70% of our atmosphere is nitrogen. So I guess that would be the easy one.
Yeah, the oxygen, I would say, is probably the key one.
Sure.
You showed some nice spectra. You showed the solar spectrum, which has this absorption line spectrum, which is typical of most stars.
Yeah.
Whereas the Wolf-Rays have these really odd-looking emission line spectrum. What's the physical origin of emission line spectra?
Well, so the difference between what we see for O stars and Wolf-Rayet stars is the optical density of the wind, or the density of the wind in general. Because so these emission line spectra they're formed through different physics. Recombination, they're called recombination lines. And recombination lines are sensitive to the square of the density. So even if the density were to change from O stars to the Wolf-Rayet stars by a factor of 10 to 20 to 50, you would easily shift from an absorption line spectrum to an emission line spectrum. So I think the answer is that both the physical density and the optical density of the winds are quite high.
So it's high density, is it?
Yes.
So, but nebulae have emission line spectra too, don't they? And are they high density or low density?
They are quite low density, but they are also, I'm not quite familiar with nebular emission, but I know there are quite a lot of forbidden lines. So I think maybe that could have something to do with it.
Yeah, plus hydrogen, that's a combination.
Yeah. Yes.
Okay, on to the details of what you did. So you were looking for binaries through the Doppler shift caused by a companion star around the common center of mass. How can you be confident that what you're seeing is the recoil of the Wolf-Rayet around the center of mass caused by a unseen or sometimes seen companion, rather than intrinsic variability in the wind?
So of course, thank you for the question. That's one of the questions that we spent a lot of time in the initial phases of the PhD trying to quantify, because these Wolf-Rayet stars, they have quite crazy winds, as they call it, and so there's a lot of variability that occurs in these winds. And if you see some wobbling of the line, is it really due to the fact that there is a companion present, or does it mean that there is just some crazy wind physics that is happening over there? So I think then what we did is, first was when we were measuring radial velocities, we had to select the appropriate lines. So we would avoid some of the stronger lines where the tops were quite variable. So we would look at some of the weaker lines, but of course that means that we needed a high quality spectra. So that was one way we decided to do it. And then the second was that whenever we measured a radial velocity, we would plot the extremes and see whether we actually see a shift in the line profile or whether it's sort of a bending. And for the Wolf-Rayet binaries that are at short periods, you of course have a lot of wind-wind collision, and definitely the spectral morphology changes quite a lot. But in those cases, there are a lot of other ways, because usually you would also see the absorption lines of the component there.
In your conclusions, you kind of, in that previous chart, you show that the WNs typically are short period binaries, very similar to O stars, whereas from your northern sample of WCs, there's a clear bias towards very long periods. So what do you think might be the progenitors of those long period WC stars?
Yeah, this is a thank you. So for this one, thank you, no thank you. Okay, so the progenitors of these long period WCs are also something that we've discussed. And so some of the things that we've come up with are, initially, this is quite not a very likely scenario, but if you would have a long triple, and then you would disrupt the inner binary, and then you would end up with a star, and in the disruption you would either end up with a merger or an ejection of the companion, and then you would end up with a long period system. But that is also not quite likely. But what I do think is that we are just sensitive, the progenitors are just long period WN binaries that we just do not see, because the variability that we find in WN stars is much higher.
My final question is, from your 1,340 spectra and your sample of 40 northern Wolf-Rayets, have you got a favorite? And if so, why?
Please don't tell them. but yeah, I mean, I think I really like WR136, because it's quite an enigmatic object, and there have been reports that it has a compact companion, but they are not like we were unable to find one. But I think we are also not looking in the right place, so maybe it exists, but we still haven't found it. So it's one of my favorite ones. Yes.
Thank you.
Yeah.
Thank you, Professor Kreuter. We then turn to our online jury member, and I hope this works because you took care of the. So
Oh wait,
not yet. So Professor Nicole Saint-Louis.
Hello, can you hear me?
I can hear you, but I'm not sure the public can yet.
No, 1 second.
I should speak louder, maybe?
I'm not sure that will help. 1 second.
No?
Just
So maybe you can repeat my questions?
yeah, I will try to. Or at least Karan can answer them.
Yeah.
I think that's the main point.
Yes, Karan can repeat them as well, maybe.
Yeah.
Okay.
So
Please go ahead.
okay. So thank you for a very nice presentation, Karan. It's nice to see you. So I'll start by a very simple questions, which you alluded to here in this slide. So you showed us a very nice evolutionary scenario for binaries, why would you expect the Wolf-Rayet stars not to be in binaries? Can you expand a little bit on some of the processes that could induce non-binarity in Wolf-Rayet stars?
Well, I think one of the thank you for the question, Nicole. I think one of the straightforward ways that you could go from an O star, which may or may not be in a binary system, to Wolf-Rayet stars that are not in a binary system, are through mergers. That is one simple way where you can disrupt the binary, or you can explain why the binary is no longer no longer exists. That's one thing I can think of in order to explain why Wolf-Rayets would not be in binaries.
But can you explain why suddenly the stars would merge?
So I think one of the physical processes through which the stars can basically lead towards a merger is the common envelope scenario, when if mass transfer occurs after the primary has a convective envelope, then mass transfer becomes a runaway process, and then the whole system is enveloped. If I can just probably go back to this. So this is sort of what it looks like. So when the whole system is in a common envelope, and then if the if the energy from the orbit can be transferred into the envelope, and if that is greater than the binding energy, then the orbit can be expelled. The envelope can be expelled. Otherwise, the friction just causes the stars to in spiral and then merge.
Okay, thanks. Is there any other process that could happen?
So I mean, either the disruption of the system. So I think there are a lot of collaborators, other researchers who are looking at runaway stars. So if the primary were to undergo a supernova event, and if the binary were to be ejected, and again the questions of kicks and everything is still up in the air, particularly for black holes, then it is possible that the binary could be disrupted, and then you would have the companion star that was previously ejected then evolve into a Wolf-Rayet star just by ejecting its own, shedding its own envelope. And then that could be one of another way where you have a Wolf-Rayet star, but which would be a runaway. And we do see a lot of these Borshock nebulae, so it is possible that these came from this scenario.
Okay, so now I'll ask you a few questions inspired by the pretty pictures that you showed. Actually, you're showing your background. I think it's a Borshock nebula.
Yeah.
But can you think of, because you have two massive stars in a system, can you think of a process that can happen between the winds in such systems that can have an impact on your observations, maybe?
So I'll repeat the question. Did you hear the question? Yeah. Okay. Yeah. So I think when there are the winds of two massive stars that interact and collide, there are a lot of physical processes such as wind-wind collisions that take place, and that can definitely affect my observations. The one thing I can think of is that if depending on the line of sight, if the no, let me think about it. So the physical processes that might affect my observations particularly, for that I think wind-wind collision would be one of the main ones, especially if these stars are close to each other. Then sort of the wind from one will interact and impact on the other, and then this definitely affects the spectra that we see, because then the spectra will sort of follow a trail of the secondary, and so that is definitely something that will affect our observations, and it's something to take into account. But then again, if this sort of a scenario were to happen, I think we would see the absorption spectra of the companion. Of course, if it was two Wolf-Rayets, then it's a different question.
Sorry. Okay, well, maybe now I think you opened the door for me to ask you a question about nebula. So Wolf-Rayet stars, some have very nice nebula around them. when you look at the nebula, do you think you can learn about binarity just by looking at a nebula?
I'm gonna pull up the picture of the nebulae so that. Hmm. Well, I mean, so I think one of the recent examples from the images that JWST put out was of the southern ring, and that's a very pretty nebula. It's a very extensive nebula, and you see that there is a binary at the center of it. You see it in the JWST image, and that was thought to be a binary for decades. And I think that definitely the bipolar structures of nebulae do definitely indicate or at least hint towards the fact that there could be a binary system. But otherwise, I'm not entirely sure if the structure of the maybe if you look at the polarization of the nebulae, that might be one of the ways to detect this. But I'm not sure about the structure per se.
Did you see the recent JWST image of one of the stars in your sample, WR137?
Yes. Yes.
Did you? Can you describe it a little bit? And do you know what the origin of the nebula looks like? Sorry, you don't have it here, but
No, I don't have it here.
it's okay, no problem. Just
Well,
maybe
I to be honest, I'm not sure what the origin of the nebula is there. For me, initially, this is what I thought, but I'm not sure this is correct. Even as well, is that basically through ejection of mass from the system in the binary would lead to some sort of a nebula that we see of the nebula that we see around WR137. But then again, I'm not sure this is the case for that particular, and I think we need to do some sort of kinematic study to determine whether that would be the case.
okay, we can talk about that another time. But certainly the image shows that it's a binary, that's clear. Sorry. Okay, well, I think I can stop here and maybe leave the others to answer questions. Thank you.
Thank you, Professor St. Louis. Then we turn to our KU Leuven colleague, Jon Sundqvist. I hand you the mic.
Thanks, and thanks, Karan, for a very nice presentation today as well. So yeah, I actually wanted also to start to ask like Paul about absorption and emission lines, but you answered that already. So but I will follow up a little bit upon it, because you mentioned that it was because they were essentially formed in the winds, these emission lines, and therefore they are not absorption lines. But our sun also has a wind. It's the solar wind. It hits us sometimes here on Earth. We can have problems with it. So why aren't we seeing emission lines then from the sun?
Well, I think the comparison between the solar wind and excuse me. Yeah, sorry. So I think the comparison between the solar wind and the wind that originate from massive stars are on completely different scales. In a sense, I think massive star winds, and in particular Wolf-Rayet winds, can be 5 orders of magnitude stronger and much faster as well. So the terminal wind speed of these sort of winds goes up to 2000 kilometers per second. So you have a fast moving wind that is quite strong as well. There's a lot of mass lost, and these velocities allow well, sort of not line de-shadowing, but so because of the Doppler shift, you're able to get a lot more photons that can create these lines, that can absorb these lines.
So why is this not happening in the sun then?
Because the velocity, the terminal wind velocity of the sun is not as much.
Yeah. It's also, they are more massive, right? But they're also much more luminous.
Luminous,
So you
yeah,
don't have
yeah.
so many photons. And then there is also, aren't there any emission lines in the sun? From the sun? I mean, formed in the solar wind?
Probably in the coronal loops and in with a lot of the magnetic fields, but I'm not well versed in these to comment on them, I think. Yeah.
No, you're also looking in the wrong way, Ben. Huh?
Yeah.
You have to look in like the X-rays to see them.
Yeah.
Okay, very good. Then I had another general there, because I also noticed that there was a lack in your HR diagram. I lacked some stars there. You know what stars?
Sorry, I can just scroll up.
Yeah, you had a very nice movie, I must say.
This one.
Yeah, and
Yeah.
also, but you can go to the next one, right? But
Yeah.
where are the Wolf-Rayet stars?
So they are over here on the left.
Okay.
They
So
go way
why
past.
aren't they on the HR diagram then?
I know it's a bit, I must say, hypocritical that I present an HR diagram and don't put Wolf-Rayet stars on it,
Mhm.
which is why I made up by putting another HR diagram later on.
Right, that's true. Why do you think they're not in the HR diagram in the first place?
Well, I think because they are quite few of them, they are short-lived, and yeah, I think these are some of the reasons that I can think of.
Yeah, actually, that was a genuine question. I don't
I
know
know,
either,
I don't know
if I'm
either.
going to be honest. So, we should put some Wolf-Rayet stars on
Yeah,
the
no,
HR
I
diagrams
know.
as well. Huh?
Definitely,
Yeah,
yes.
definitely. All right. Then I did have some specific here, because you talked about your, obviously a really interesting result in your thesis is the 3 out of 12 long period binaries, right? Which you draw some really interesting conclusions from. But is it really large enough? You introduced us to Bayesian statistics, right? But you sort of walked away a little bit. Yeah, but we do see more on the southern hemisphere of them. So why is that not taken into account then in your statistical analysis? If you already know there are more short period binaries in the southern, in like your priors, or
so I think that's a very good question, and I think the reason we could not do it just by taking all of the Wolf-Rayet stars from the literature, and the fact that we had to start our own survey, was basically when we are correcting for observational biases, you really need to know everything about your sample and your observing strategy, your sampling, the time sampling, the baseline, the normalization, all of the data analysis from scratch, and that's only then can you actually correct for observational biases and be sure of it. So which is why we take inspiration from the literature, we take the derived periods of it, but we don't take the spectra, because of course there are a lot of spectra that are available even via ESO or even from other facilities over here. But the reason we do it all is to get sort of a homogeneous process of normalization of the spectra, because as you are well aware, the normalization of the spectra for Wolf-Rayet stars is quite complicated. So A, the normalization, and B, measuring radial velocities. So the techniques used to measure radial velocities in a lot of different studies are different.
that being said, even though you could say that you have only worked on a subsample of the total Wolf-Rayet star population, it seems, should there really be a bias between the northern star and the southern? I mean, if we look at Paul's new catalogs, there are quite a lot of Wolf-Rayet stars now, significantly more. So if you were able, this would have to be like an educated guess, you can call it. What would you think? Would your sort of qualitative distribution still hold up if you were to be able to do this analysis on a let's say a sample that is representative for the full WC population in the galaxy?
Well, in that case, I would actually just go down to my plot over here. Yeah. So I think that if you were to include a representative sample of both the north and the south, you definitely have a few more short period WC binaries, and that would probably skew the distribution more towards, little bit more towards flat, but you would still see a discrepancy between the WNs and the WCs. That is something I think will still hold up, even if you were to expand the sample and take a more representative sample. I still think that you would see at the most conservatively a flat distribution. But I think there's one more bias, is that for the long period WC binaries are dust producing systems. So we are able to identify more of them as compared to the long period WNs. That being said, I think that with the quality of data we have, we are still able to identify long period systems with spectroscopy. It just takes a long time to do so.
So essentially, the qualitative conclusion should hold up,
Yes.
if I understood you. Okay, yeah, that's indeed genuinely interesting. And then I apologize if I repeat this from the internal defense, but in your WN here, we didn't talk about this, but there are also WN Wolf-Rayet stars, which are not believed to be very evolved, right? Which could be from other types of evolution channels. Are they in your sample or in your, say, what you're basing your statistics on? Are they included, or have you been able to separate these, that there might be different natures of, say, what we then in our field call WNH stars or standard WN stars, which you can compare to the WC stars, right?
Yeah. So I think the difference over there is just the challenge is to identify the presence of hydrogen in the spectra. And usually these WNS stars, which are on the main sequence, they are also quite luminous. So as we discussed during the internal as well, so one way to do it would be to some sort of say that anything more luminous than X, and X is whatever choice you would like to, would anything more luminous than that is probably a main sequence Wolf-Rayet star. Another way to do it, as Paul suggested, would just be modeling of these stars and just to see whether they have hydrogen present in the spectra. And so far in my sample, I think there there's one candidate WNH, which is WR148, but it's also in a binary, and it's unclear. It looks like it's on the border of 10 to the power 6 solar luminosities. So if you were to ask me, I would, in my naivety, because I'm not an expert in spectral modeling, I would say that it's not a main sequence star.
Okay, yeah. So then we can try. Can we then also? Does that mean that we can trust, so to say, your overall statistical distribution as well? You think then?
I think it should hold up. The uncertainties will definitely shrink as the method improves and as we expand the sample. So that should definitely help. But for now, the general takeaways should remain the same.
Okay. Thanks. Yeah. Okay. And then I had perhaps a last question here, and that's I mean, you brought this upon yourself. I'm sorry about that, but you were talking about the aliens, huh? And yeah, but it is true. As astronomers, we have to pay attention to the exoplanet community. Extrasolar planets are, of course, just the planets around other types of stars in our sun. But again, I have not seen any exoplanets around the Wolf-Rayet star. Why do you think that is?
The formation timescales are just not long, and like the formation timescales are just too long. Wolf-Rayet stars live for about 50,000 years or so, and 50,000 to 100,000 years. But planets.
But if they're
take much longer.
evolved star, couldn't they be there from the beginning and then just
But again, massive stars, their lifetimes are so short. They live fast, they die young, they go out bright with a bang. They live so short that even then the formation timescales are not long enough for planets to form.
Okay. Yeah. Thanks.
Yeah.
Thanks, Professor Sundqvist. And we turn to the supervisors, and I will first hand the floor if you would like to our foreign supervisor, so Professor Chenard.
Yeah. Hi, Karan. Thanks a lot for this beautiful presentation. I have one real question and one question that I'm not sure about the answer, and the other one that I am sure about the answer. So I won't tell you which is which. So when you do the bias correction for the carbon-rich Wolf-Rayet stars, you mentioned the fact, you explained Bayesian statistics, and you mentioned the fact that you detected 3 carbon-rich Wolf-Rayet stars in binaries, but because it's kind of unlikely to have detected them, the biases are against us. We are probably missing a few more. That's what's pumping up your binary fraction. But there's also another interesting thing. I mean, in the binaries that you do detect, you don't only detect the radial velocity motions, you also, correct me if I'm wrong, see the companions in all of them.
Yes.
I mean, this is not what your method was based on, but you do see the companions in all of them. And in the other ones, you don't.
Yeah, it's a good bonus.
Do you think it's a coincidence?
It's definitely it's like patting yourself on the back with one hand, because like, yeah, definitely we do see the companions, but it could just be that the systems are oriented in the right way and that we are lucky, but then we don't see them for the others. But I think it could also be about the light ratios, could also be about the separation. It is not so clear then. I wouldn't be quick to jump on that ship.
Okay, thanks.
Yeah.
Second question. So this Wolf-Rayet phenomenon, you mentioned that it starts occurring when the stars become hot and get rid of a lot of their outer layers. And now there is also the lower mass equivalent, right? The subdwarfs. Many subdwarfs are known. They don't show emission lines at all. So what's the fundamental difference between those and Wolf-Rayet stars?
I think it's the luminosity. The main thing that you can use to differentiate them is the luminosity, and that's because the higher the it depends on metallicity as well. But depending on the luminosity and the metallicity, they need to have winds that are strong enough to drive this dense matter away from the stars. So you could have a subdwarf in the space where you would expect a Wolf-Rayet star, but slightly less luminous. But if the winds are not strong enough for it to drive away a Wolf-Rayet like wind, it will be there, but it will simply not appear as a Wolf-Rayet star.
But there are also the central stars of planetary nebulae. They have lower luminosities, and yet they do show very strong Wolf-Rayet spectra.
Yes, but then so these kind of objects, it's believed that the strong winds that originate from them are due to either a late thermal pulse or it's a very short-lived phase, the central star of planetary nebula appearing as Wolf-Rayet stars. So I think that's not the norm for these kind of objects.
Mm-hmm. I agree with the luminosity, but the mass is probably also important. Yeah. So the luminosity to mass.
Yeah, mass.
Thanks.
Before turning to the public, I invite Professor Huxana.
Maybe one question that we did not discuss, but we've been working on this for 4 years, and of course, at the end of a project, there's always lesson learned. Is there anything you said, oh, we should have done it differently, or next time I start a new project, I'll pay attention to that specifically? I think your answer is also important for the other students in the audience.
Well, I think particularly, is this related to particularly this project or just in general?
You can use your academic freedom.
Right. So for particularly this project, if I were to do this all over again, if I were to go back to the beginning, I would get a lot of high cadence data for each and every Wolf-Rayet star. That's something I would definitely do right straight out of the bat, just because it then becomes easier to do a star-by-star investigation of their variability. And that gives us more confidence, because right now we've done it for 1 or 2 stars and generalized it to the entire sample. But I think it would give us a lot more confidence, and also to our colleagues in the community, that we were doing a decent job if we were able to do this from the very beginning. Yes. Apart from that, I don't have any other complaints. No.
Okay, thank you.
So, as this is a public defense, I would like to invite you to ask questions to Karan, please. I will try to walk around with the mic.
Hey, Karan.
Hey.
Can you maybe go to the plot where you had these 2 threshold velocities, like 30, yeah, something there. So you were telling that it took a lot of thinking and then discussing where to take this threshold.
Yeah.
But it looked like a very easy way out. On the right, the ones confirmed by the binary, by the literature. On the left, not. So, and in the end, you also said, it actually doesn't matter. So why even take this threshold then? Like,
so I think it's more illustrated by the right plot as compared to the left plot. I have my pointer here. Yeah. So basically, in this sort of a plot, when you have a large number of objects, you expect a certain radial velocity variation due to Doppler shifts, and at some point you expect some small radial velocity variations due to either the inner physics of what is happening within the star. For B stars, it could be like pulsation or whatever it is. They will definitely affect your measurements. So if you start from the right and go to the left, you can sort of fit 2 different lines So one that goes straight down from the left, and then one that goes sort of horizontally from the right. And a lot of studies have used the intersection of these lines as the threshold, right? And that is one way to sort of physically explain what we are seeing on the plot. Sadly, this cannot be done for this, obviously, because A, we don't have enough objects, and B, you see your method does not work here because we have WR119, which outlier. Actually, this is a dust producing system, dust producing WC star. So I think a lot of experts believe that it might be a long period binary. So yeah.
Okay, thank you.
Any more?
Hey, Karan.
Hey, Matthias.
Why does the universe conspire to put more WR stars in the south? Is there any particular reason?
Well, we're looking at the galactic center, star forming regions,
Okay, so
etc.
star forming. Yeah,
Yes.
makes sense.
Hey, Karan. Congratulations on this great work.
Thanks.
So I have two questions. The first one, did you derive any of the orbital periods, or are they all from the literature?
So I didn't derive any of the orbital periods, but we have enough data to do that for some of the short period systems.
Okay. So are you planning to do that?
Yes, at some point.
Great.
Yes.
And the other question is, can you go back to your conclusion slide?
This one.
Yeah. So I thought that you were very cautious with your
Yeah.
conclusions, and that's good. But I'm wondering. So in the case of the WN stars,
Mm-hmm.
they have a peak at short orbital periods, and so that peak for all stars, it's mainly for stars or binaries that haven't go through mass transfer yet, right?
Yeah.
So do you think that could be telling you something? So could it be that the WN Wolf-Rayet stars are the ones that are coming from the single channel, and maybe the other ones are product of binary interaction?
That's actually a very interesting question. So I think in the past, like when these stars were first identified, it was thought that WNs evolved differently and WCs were a completely different beast, let's say, right? But then a lot of modeling, stellar evolution modeling, especially in the 90s, 80s, and early 2000s, showed that in order to get a WC, you need to pass through the WN phase. So then the WNs and the WCs are definitely linked. And so I think in order to explain the distribution of the WN sample, you can say that yes, if mass transfer were to have occurred on the main sequence, then the shift in the orbital periods would be a factor of a couple, 2 to 3 at most. So then that is sort of consistent with what we see in our period distribution. But the same from the WN to the WC doesn't check out. The shift is just way too much.
Another one, Karan?
All questions start with hey Karan, so hey Karan.
Yeah.
You looked at binaries, but you always talked about the Wolf-Rayet part of the binary. When you looked at the companions, what was like the main type of companion that you found? And does that give you any kind of extra information about what the evolution was, or maybe more information of why you get certain Wolf-Rayet stars or not?
Yeah, thanks for the question. That's another thing that we see is that a lot of the companions that we have are late type O stars. Late type, or some of them are early type O stars. And that's just in our sample. Of course, in other galaxies and other objects in the south, they also have like early type or early O type companions, and there are also some Wolf-Rayet plus Wolf-Rayet binaries as well. I think we are biased towards seeing the more massive companions, because they are just simply more luminous, and then you could see them in the spectra. But if you were to have a Wolf-Rayet star and the sun, the Wolf-Rayet star would be much more massive, and so wouldn't move much in the orbit itself. The center of mass would be very close to it, and so you would not see a lot of radial velocity shifts, and you would not see the sun in the spectrum because it's way less luminous as compared to the Wolf-Rayet star. So I think we are definitely biased towards seeing O stars and maybe some B stars, but they definitely exist. Maybe they exist.
Okay, thank you. Any more questions from the public? Yes. Good for my condition.
Hi, Karan. It's
Hi.
slide 35. This is your model's predictions after the Monte Carlo simulation, and you have the priors, right? I have the question for the WN binaries.
Yeah.
The literature data points, they're a bit out of the credible interval. It's because of the uncertainties, measurement uncertainties, or is it some other reason?
Yeah, I think it's definitely, that's a good question. Thank you. Yeah. So the data we measure is out of the credible interval, and that could be because the credible interval that we see here is based on certain assumptions from our models. And it could be that assumptions need to be slightly modified, but I don't think so. But no, notwithstanding. So these are the observed distribution of binaries, right? And it's not that our model is actually fitting this data. Our model doesn't fit this data. Our model corrects this data that we observed for observational biases. So this is the intrinsic distribution, and this is what we observe. So we are missing a bunch of stars, both at slightly shorter periods and at longer periods. That's what this shows.
Okay. More questions from the public? If not, I think it's time for the exam committee to gather for the deliberation, and we will come back after the deliberation.
It's coming.
Okay. Ladies and gentlemen, dear colleagues, I will now proclaim the result of deliberation by the exam committee appointed for the doctoral degree in science, astronomy and astrophysics. Mr. Karan Dsilva has presented to the Faculty of Science his PhD thesis on the topic The Multiplicity of Galactic Wolf-Rayet Stars. In partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics. And he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Karan Dsilva the degree of Doctor in Science, Astronomy and Astrophysics. Congratulations, Karan.
Thank you.
Also, congratulations to two supervisors. This is
Yes. Thank you. Oh, this is your pen? Yes, okay.
this one. I hereby officially close the session.
Oh.
I can read myself. Is it on? Yes.
Yeah.
Well, I think the roles are reversed because in the last 4 years you have had to try to read my handwriting and it's a challenge, as my students know. And now I have to do the same. But I mean, Karen, certainly congratulations. It's always a pleasure to be the first person to congratulate, as a promoter, to congratulate the new doctor. So what I can say, if I look back, it's always been a pleasure to work with you. So looking at the little in the history, so you've been hired in September 2018, if I got my math right. So that was 4 years ago. But we knew each other before that because you had been following the second edition of the course Binary Stars that I gave in the part of the Master of Astronomy and Astrophysics. And one of the things that I'm trying to teach to the students is to struggle their way through an astrophysical data set. And so you did well. So when you applied to the PhD position, I thought, well, good, this is a guy that likes to struggle with data. And I think that in the years to come, you had to do that, and you did that well, and it was not always easy. I mean, most of the time it was not easy. But I think that has been a great quality that you showed, is the persistence, the different elements that you can bring together in the code, and also that you understand what you're doing, as always, because you don't try to use things as a black box, but you try to understand the details. And of course, Tomer and I and other colleagues were also there to nudge you to go each time a little further in the understanding of the project. So you explained that during your presentation, but you collected over 1,000 spectra of a few dozens of Wolf-Rayet stars. But not only you collected data for yourself, but you contributed to a lot of projects of the IVS by going to La Palma, doing service mode observations for the others, and also advising people how to analyze Hermes data. Your topic was, of course, the Wolf-Rayet stars, but to do that, you not only obtain data from your Wolf-Rayet stars, but you also help improving the overall quality of the final products of Hermes, because you implemented a method which is correcting for the instrument response curve. and you spent most of the first year, maybe even part of the second year, to finalize that, and that's also a legacy value for our own telescope. And you combine that with new cross-correlation methods, not something that you developed, but you implemented it fully to precisely measure the radial velocity of Wolf-Rayet stars. And then also you implement another method, which is using MolecFit, which correct for the observational features, absorption features that are not due to the stellar spectrum, but to the Earth spectra, because we are our own observations are polluted by the Earth's atmosphere, and you can correct for that. So just to show that you can bring a lot of different elements together. And I think that's part of the reason that you have been selected for your next challenge in Brussels, starting in just 2 weeks from now. So people will be looking forward to that specific set of skills. And I'm sure that you will do well in your next endeavor. Now, if I look a little in the personal side, always been very pleasant to work with you in a positive way. Yeah, you come with new ideas, a lot of enthusiasm, a lot of energy. I've been also asking around what could characterize you, and they come up with 3 words. The first one is food. And I knew that if you, I mean, just out of interest, open the thesis of Karan to the acknowledgement part. If you look at the first 3 pages, there's 12 times the word food in it. The second one is D&D, and I think that holds for double degenerate binaries. And that's also something you contributed to, is our search for black holes as a side project. So that's another contribution you did. And the first word, the last word was chess, and I'm sure that we will hear more about that in the reception later. So I'm not gonna spend more time. I know that in the last year, there's another word that you did not mention, but this is stress. And that's something that everyone struggled, especially PhD students in the last year. I think I've told you, and I've told, if not to you, to other students, this is part of the process to manage the stressful deadline of writing a thesis. But to help you, now that you are over that, to recover a little, Tomer and I get you something. It's a little outside of your comfort zone, I've heard, but try it and try to get rid of all the stress that you have accumulated over the last few years. Great. Thank you again for your work. It's been a pleasure to work with you. And yeah, we'll be looking to see what happens to you in Brussels. And that's not too far away. So you hopefully come back to see us in Leuven on a regular basis.
Thank you so much, Hugh. So of course I have not prepared anything because I've been busy with other things, but definitely I would like to say a few words. I'd first like to thank Hugues and Hans, I think, because you were my supervisor during my master's and you during my PhD. And I think without the two of you, I would not be the researcher I am today. So I'd just like to thank both of you. And of course, Tomer and Jacques as well. I would also like to, like, me coming to Belgium was a very, let's say, spur of the moment kind of thing, because so my good friend Adi was sitting at the back. So the two of us during our bachelor's, we would sit together in a tiny room and spend every Sunday applying to universities abroad to try and see where we could come for our masters. And someone randomly, I mean, we were looking at Germany, we were looking at the UK, because we never heard of KU Leuven in Belgium. And then somebody was just like, oh yeah, why don't you check out KU Leuven? And I was like, okay, wow, this is a great place. And then we applied, and then we got in. But then Adi also got in, but he applied for the wrong program. So we were supposed to come to university together. So Adi, Kanaka, and I were supposed to come to university together, but Adi applied for the wrong program, and so I ended up choosing a university in the Netherlands. But oh well. So yeah, I mean, I've thoroughly enjoyed my life here in Leuven for the past 6 years. I've met so many friends, and I I cannot even begin to tell you what an amazing group of friends you've all been. So throughout the pandemic, throughout the lockdowns, throughout even pre-pandemic stuff, people who have introduced me to Belgian beer. I think Gwenel is sitting somewhere over here. Yes, he was the one who dragged me across every pub in Leuven until I found a beer that I liked, and I never drank before I came to Belgium. So it was quite a challenge. And then, of course, as Hugues mentioned, food is a very integral part of me. And I enjoy exploring and discovering a lot of food places. And I think Leuven has been the best place to do that. But more than that, I think the Institute, because Hugues and everybody else at the Institute has always made it a very welcoming and a very inclusive place. And for that, I'm eternally grateful. Because my first day of the Masters, we were sitting with, I think, another 8 or 10 Belgian students. And when the professor would ask a question, nobody would say a single word. And I was like, oh my God, where have I come? And yeah, but thankfully the people at the IVS, all of you guys have made life extremely extremely happy for me over here in the past in the many years. And I hope that I'm still going to be in Leuven, even though I'm going to be working in Brussels. So I hope that I will still see all of you around, and we will still go to play a lot of sports and hang out in the city center as well. And that being said, I have a few things for you and for Tomer as well. So you might need to hold it from the bottom because this is also for you. Thank you. Yes. Thank you guys so much. Oh, you need to hold it from the bottom. Yeah. Yes. Just some tokens of appreciation from India. I really hope you like them, and I really hope that I'm sure we'll keep in touch because I'm still here in Leuven. But now we have an amazing reception waiting for us outside. So without any further delay, thank you so much, everybody.